Hi, folks. Welcome back to Father-Offspring Interviews, episode 53. Getting right into it, we are going to start with a topic that we've gotten a number of questions about from Andrea from Canada, Ina from Russia/Lithuania. Professor, why do we dream?
Well, that immediately brings up two questions. The first one is why is the kidney a kidney-shaped organ? And the answer to that is nobody knows. But the second one is why are dreams dreamlike? And we actually know the answer to that. And it's got to do with what's going on in your brain when you sleep. Sleep involves all these different sleep stages picked up with electroencephalographic information, probes on your head. And what you see is over the course of sleep, you descend through different stages. Probably the most characteristic one is slow wave sleep, which is when most of your brain is close to being inactive, which is when you are doing the most energy restoration in your brain. But then the sleep stage that is so interesting is the one where you suddenly start twitching and your eyelids move rapidly and you've gone into REM sleep, rapid eye movement sleep. For the moment, we will grotesquely simplify and say REM sleep equals dreaming, and that's not the case, but hold on to your hats. But REM sleep. REM sleep is really interesting because of what happens in the brain. Just before that, you're in slow wave sleep. Most of your brain is a very low metabolic rate. You go into REM sleep, and suddenly everything wakes up in your brain. Your motor pathways, your cortex, your limbic system, your autonomic nervous system, your heart rate's increasing. You're like getting ready to move your limbs. Your eyes are blinking. Remarkably, when you're in REM sleep, some parts of your brain are more metabolically active than when you're awake. So, two interesting details about that. First one is among the areas that get very activated is your visual cortex in the back of your brain, but in an interesting way. Normal deal. You look at something, and the very first layer of your visual cortex activates, and its job is to detect pixels. And then it sends information to the second layer, which turns the pixels into lines. And then the third layer, which makes the lines moving in these layers of sort of feature extraction until umpteen layers up there, you're beginning to see complex images. When you are in REM sleep, your visual cortex activates, but not those really nuts and bolts first levels down at the bottom there. What activates is already a number of levels up. What's that about? Your visual cortex is not activating because you're looking at something. Your visual cortex is activating because you're having visual stuff going on in your dreams. Your brain is directing dreamlike visual information way many levels up there. Okay, so that's cool. But the second thing is not just that you're getting your sensory information activating many layers up. Your brain is telling you what you're seeing instead of the outside world. But amid most of your brain now being very active during REM sleep, one area turns off. One area goes completely silent, and that's the prefrontal cortex. Prefrontal cortex, you can recite along with me by now. Prefrontal cortex, it's the coolest part of the brain. It does self control and long term planning and impulse control and emotional regulation. And it's the newest evolved part of the brain. And we've got more of it than any other species. And it doesn't fully develop in us until we're 25. Your prefrontal cortex makes you do sensible, prudent things. And what happens during REM sleep? Your prefrontal cortex goes completely silent. It goes offline. And suddenly you're dreaming that you can breathe underwater or fly, or you're starring in some Buzzley Berkeley musical or something. And that's why dreams are dreamlike. That's why they're gibberish and nonsensical and all sorts of things which you would never want to actually do in real life. It's because your prefrontal cortex is completely offline. So that tells us something about why dreams have dreamlike quality. But the question is closer to, why do we dream at all? What are dreams about? And predictably, because it's close to impossible to get a clear answer to that, there's been a gazillion different theories out there about that. Um, and they fall broadly into a number of categories in addition to the ones that are way out there in the lunatic fringe. Okay, somehow try to organize these together. First thing is REM sleep and dreaming is not synonymous. There's lots of times when you are in REM sleep when you are not dreaming. And there's times that you are dreaming when you're in a non-REM state. So they're not absolutely synonymous, but we'll give that one a pass and say in a rough kind of way, they kind of go hand in hand. So why do we get REM sleep where your brain becomes more active than places during everyday life? And you've got this dream stuff going on. So there's a bunch of theories that are built around the notion that what you're doing when you're dreaming is reviewing stuff from the previous day. And that takes a number of different flavors. Francis Crick of Watson and Crick DNA, who spent his last decades deciding very correctly that the brain was much more interesting than DNA, had a theory about dreaming. And what it's about is you are going through what you went over today. You are reviewing the day. And the purpose of doing this is to jettison the gibberish, the nonsense stuff that you really don't need. It's a cleaning out the day's recycling before tomorrow comes along. That was his notion. Meanwhile, a very different flavor comes through with a lot of theorizing about dreams are about reviewing what went on earlier today. One idea is dreaming is when you rehearse, when you practice, where you consolidate, where you reactivate some of the interesting things that happen during the day. Okay, that's great. So, how do you know that's happening? And some really intriguing findings. You put someone on a brain scanner or EEG stuff, and you're recording activity in different parts of the brain, and you will see a particular pattern while something interesting and compelling and exciting or whatever is going on during the day. And then you'll see at night the same pattern repeats. It's like you're replaying it to consolidate it, file it away from memory. This is a form of practicing so that you're all ready the next time something like that occurs. What this leads to is this very, very trendy field. And this was mostly started by a psychiatrist at Harvard named Alan Hobson, who said that part of what you're doing during sleep is learning. Learning happens especially during REM sleep, especially in association with dreams. So, what's the evidence for that? Why have dreams? Why, if it's facilitating types of memory, you're consolidating by replaying it, going through the same spatial confirmation of which neurons are excited, you're ingraining it more. You will remember it better. But this was taken one step further by another Harvard psychiatrist, Robert Stickold. And what he began to focus on was the notion that not only is REM loosely synonymous with dreaming, not only is it good for remembering stuff, it's good for problem solving. Now, not just any kind of problem solving. You don't dream like which column you take the deductions in when you're filling out your taxes, that you figure that out. No, dreaming solutions to problems. You go to bed with some like quandary on your mind. And in the morning, it suddenly seems clear. You have figured out what the solution is. You have figured out what you want to do. But then there's a whole other school of theorizing about what dreams are good for. And this is the notion that what you should be doing when you're dreaming is exactly the opposite of what your brain has been busy with during the day. And this is sort of a notion of like use it or lose it. So you've been sitting there and you spent all day long doing nothing but math equations and thinking about sensible things. And by the time you go to sleep, the part of your brain that generates nonsensical gibberish hasn't done anything during the day and it needs some aerobic exercise. In this sort of view, what dreaming is about is to activate parts of your brain and thus typically some irrational parts of your brain to activate them to just sort of keep them up to speed, to keep the battery from running down. And what that predicts is you get somebody who spends the entire day in a rehearsal for some nutty, surreal play or something. And that night, they're going to dream about balancing their checkbook. You're just balancing which parts of your brain did a lot of stuff during the day and which parts didn't. Give those parts a little bit of exercise at night. Now, this was elaborated on a few years ago by a neuroscientist, Dave Eagleman, who's a colleague of mine at Stanford, who took this one step further. So, if you don't use parts of your brain for long periods of time, they atrophy in this very literal sense. They will retract neuronal processes. They will disconnect synapses if you're not using them. And in this wasteland of benign neglect, neurons in other areas will now grow in projections to take over this area because it's not being used. And what he focuses on is the fact of this sort of invading under-exercised parts of your brain occurs a whole lot faster than people used to think. It could happen over the course of hours. So his notion is dreaming is not only to activate parts of your brain that you didn't exercise during the day because it's good to give it some exercise, take it for a walk, but also what he explicitly calls a defensive strategy before some other part of your brain decides, whoa, this like ridiculous, surrealist dream part of your brain hasn't done anything today. Let's just take it over. Let's grow some axonal projections and use it for our purposes. Run it during your dreams. And that perks things up and makes it clear this is an active area. So that's an appealing sort of theory that's around these days also. As evidence for it, this notion that, ooh, you got to exercise the parts of your brain that didn't do anything during the day because your brain is so plastic, neuroplasticity. It is so neuroplastic that it'll just seize that opportunity and take over that area. What he sees is across a whole bunch of different primate species, the more neuroplastic the nervous system, the more dreams dominate REM stages, the more you have to do this defensive thing. Okay, so why do we have dreams? It's to review what went on in the day, to get rid of some of the nonsense, to reinforce some of the important memories, to do some problem solving, and seemingly the exact opposite theme, to also exercise the parts of your brain that didn't do much during the day. That's the state of the field. Nobody is in much of a position to prove which one is absolutely right or wrong. And you're probably on safe ground saying nobody knows, and it's probably for a bunch of reasons. And make sure you use the word heterogeneous somewhere in there. That's kind of the state of the field.
All right. Next, Mirna from Croatia asks, what do you think of Neanderthal DNA being implicated in autism susceptibility?
Oh, I think it's great. I think it's great. And I also think it's probably being overblown. Okay, Neanderthals, over the last 100,000 years or so, humans, modern humans, Homo sapiens, shared parts of the planet with at least two other human species. Neanderthal, everybody knows about them, predominantly in Europe. We seemingly drove them to extinction 30,000 years ago or so. Meanwhile, over in Asia, there was around the same period another species of human, the Denisovans, first identified in a cave in Siberia called Denisova, was another species of human where they've extracted the DNA from the very small number of bones that have been found now at a number of different sites in Asia. And they're kind of like Asia's Neanderthals. Around the same time that humans were going about their last 100,000 years, there were significant stretches of time where humans in Europe were encountering Neanderthals and humans in Asia were encountering Denisovans. And, they get together and one thing leads to another. And what's been like one of the great irresistible smutty things about paleogenetics is there was a lot of mating between humans and Neanderthals and humans and Denisovans. And at this stage, the number that always comes through is people of European ancestry. 4 to 6% of their DNA is Neanderthal derived. People from Asia, in particular East and Southeast Asia, about 4 to 6% of DNA is derived from the Denisovans. There was probably another group of humans running around then called the Hobbits on this one island in Indonesia, which I love, but we will not get to here. Okay, so humans interbreeding with Neanderthals, interbreeding with Denisovans, and in the process, certain Neanderthal genes and certain Denisovan genes entered the human gene pool. Not all of the human gene pool. Where did this not happen? In Africa. Because humans left Africa long, long after Denisovans and Neanderthals were running all over Eurasia, humans coming out either in one or a number of migrations 80,000, 60,000 years ago or so, and crossed over into Eurasia and encountered these other species. People living in Africa never encountered them. There is no admixture of Neanderthal or Denisovan DNA into people of African ancestry. Okay, so Eurasians have some Neanderthal DNA, in particular Europeans. And what is some of the DNA that we've gotten from them? One of the more solid ones is it seems like being red-haired and having freckles was a Neanderthal trait that got into humans. That seems to be mostly rooted in Neanderthal DNA. So that's kind of cool. But what the question is alluding to is some sudden hints in the literature that genes relevant to autism got into the human gene pool by way of Neanderthals, by interbreeding. So, what's the evidence for this? And I think the most prudent way of saying it is at this stage, it's a little bit subjective. It's a little bit suggestive, but don't get all excited about it. First piece of evidence is really, really indirect. And this was a study that kind of, I think, stretched things too much. They noted that there's higher rates of autism, or as termed these days, autism spectrum disorder on a continuum of neurotypicals and neurodiverse. But nonetheless, the incidence of that is higher in Eurasian populations than in African populations. Whoa, how do you explain that? It's obvious. What's the difference between Eurasians and Africans? Eurasians had sex with Neanderthals and picked up genes from them. Basically, this is gibberish because you could make the same argument. Whoa, not only do Eurasians have higher rates of autism, but they have higher rates of speaking Finnish and Mandarin than do people from indigenous African populations. It must be because of the different languages. Yeah, just sheer correlation. So this was a study that got some degree of attention, but this is very, very preliminary. The next study that's pertinent is really, really intriguing. And it has to do with one of the amazing, cool, creepy things you could do with neurons, which is you take neurons out of a fetal brain and you sort of separate them. So you've got this whole slurry of neurons and you throw them into sort of this soup of nutrient broth. And what you'll see is over the subsequent days to weeks, these random neurons that are just bouncing around there and bumping into each other, these random neurons that could be from a mixture of different brain tissue donors, so they're unrelated, they begin to self-organize into structures. structures that bear some resemblance to mini versions of brains. And these are now called brain organoids. And you give them a while to do that, and they start forming something that looks like a cortex, and they start making something that seems like cerebral spinal fluid, and they start having very rudimentary baby steps of electroencephalographic activity. Whoa, are these tiny microscopic little things like little starts at self-made brains, at consciousness? This seemed ludicrous 10 years ago. This is a real topic of conversation at this point, including at what point are you obliged to pull the plug on your organoid, and how can you tell that's happening? But in any case, the notion that organoids, without any blueprint, without anything in charge, self-organized, jargon in the field, emergent complexity, began to self-organize into these structures that looked a little bit like mini brains. So, one of the leaders in this field, neuroscientist named Alison Watry at UC San Diego, did a really interesting experiment. Their group took a gene that's specific to Neanderthals and took some of these neurons that were about to be tossed into the soup to go about making an organoid, and knocked out the human version of that gene and substituted in the Neanderthal gene. And not just any old gene, but a gene implicated in brain development. Whoa, okay, what's going to make this story blow through the roof in terms of, and you put in the gene and all these little organoids developed autism spectrum disorders? No, that's not what they saw. What they saw was the brain developed a little bit slower than when it was only human genes, and it looked a little bit different, and people conjectured out the wazoo, but the basic conclusion was you stick a Neanderthal gene in there relevant to brain development, and something or other looks different. So that's as far as that story has gotten. But the one that really has to catch your attention is one that came out in the last year. And what that's about is looking not at genes, but something called SNPs, SNPs, single nucleotide polymorphisms. This particular spot in this gene is a hotspot for variability between people. It's a polymorphic site. It's one little letter, a single nucleotide polymorphism. And people have been exploiting this for years, just looking for patterns of these SNPs. And there are millions of them scattered throughout the massive genome. And you look for patterns of them to see things about relatedness and things about similarity of gene evolutions. And so that's a whole science. Okay, so looking at SNPs, what people noticed was people with autism, people on the autism spectrum, people, family members on the autism spectrum. And there's lots of evidence to believe that the genetic component to it is coming through in a milder version, often in family members. What you look at and what you see is people in the autism sort of end of humanity have a higher than expected rate of SNPs that come from the Neanderthal genome. That's it. That's the state of the field at this point. And naturally, as soon as that came out, there's all sorts of people speculating, did Neanderthal social behavior have more autistic-like qualities than Homo sapiens social behavior did? And what was the advantages of that in their world? And it's built around the fact that as people have accepted more and more, not only is autism spectrum disorder on a continuum, but it has, in I would opine here, other than the most severe cases, some advantages, some strengths, some realms of idiot savant is sort of the pejorative description of it. There's pluses and minuses to how much you were devoting your brain to social relations versus to systematizing type stuff. So, were Neanderthals, their social world more benefiting from autistic like cognition than Homo sapiens? At this point, that's sheer speculation. For my money, the coolest thing is this recent finding. People who genetically carry a high risk load of autism spectrum disorders have disproportionately gotten genes from Neanderthals. That's it. This is not saying there are Neanderthal autism genes. This is, just looking at statistical patterns, but it's really interesting. So I hope people follow up on that a lot in the future.
Finally, Andrew from Ohio asks, why is social anxiety a thing? How does such an evolutionarily backwards thing exist?
Well, anxiety, the most common psychiatric disorder on earth, followed close behind by depression. Anxiety, first off, getting a definitional sense. What's the difference between anxiety and fear? Fear is when you are being threatened by something real. Anxiety is when you are perceiving threats that are not there, that other people don't, and that thus comes with some characteristics. The thing about fear is it's demarcated, and thus, if the fearful thing is taken care of, you can stop feeling fearful. The thing about anxiety, it is non-specific enough that it could just seep on and on. What's the difference between anxiety and depression? What anxiety is about is you are seeing threat, you are seeing menace, you are seeing loss of love, you are seeing all sorts of adversity, and you believe you can still cope with it. What you do when you are anxious with neurotic, anxious coping style is you come up with 14 different coping responses all at once, and they're all mutually contradictory and they make things worse and they're not effective. And that's, but you're still trying. You're in a froth of excitation, hyperactivity of trying to solve this seeming menace. What's depression about? Depression is when you are still perceiving the same thing as being there, but you've given up. Anxiety is a brush fire. Depression is this smothering quilt that's weighing you down. Okay, so anxiety, that's sort of its place in the world. And of course, there's multiple subtypes of anxiety. There's general anxiety disorders, there's panic disorders, there's all sorts of them where people debate whether these should count as anxiety or as a cousin of the categorization. But admit that probably the most common subtype is social anxiety. Social anxiety, what is that about? It's where you attempt to avoid social situations because you are afraid of being judged negatively, where you were unable to become comfortable around strangers, where novel social circumstances put your stomach in knots. What are sort of the three official building blocks of social anxiety? The first thing is you don't habituate to novel circumstances, to novel people, because again, this is about sociality. You don't habituate. You don't learn the social cues that tell you that this person is benign, this person is nice, this person, in fact, approves of you, likes you, whatever. And third, you're not as motivated by the rewards of sociality as you see in most people. And you put those pieces together, and that's the building block of social anxiety. Now, the interesting thing about it is that third one, yeah, you don't habituate to strangers, you don't learn how to recognize that they're actually benign, all of that. You don't get as much reward out of social interactions as most people do. That's subtle because that's not saying you are less capable of being rewarded by sociality. It's saying something very different. People who truly are not rewarded by sociality become hermits. The thing is with people with that social anxiety disorders is they are rewarded by social pleasures and stuff. But the thing is, they are so yearning for it. They are so worried that they will not get it. They are so insecure about being judged for who they are that it simply makes it impossible to experience it. What social anxiety is not about is having no need for humans. It's having such a desperate need for socialization and bringing so many distorted cognitions about how you are going to be perceived that it makes it impossible to get any pleasure from it. So all of this within a backdrop of, at the same time, these are not people who are atypically anxious about spiders and snakes and being dangled by a bungee cord over a big ravine, and it is very specific. Now, the neurobiology of it also shows that specificity, and that you see things like the amygdala. We know all about the amygdala, fear and anxiety and threat and aggressive responses and fleeing responses, and the amygdala about all sorts of bad stuff. And what you see is you take your average person and you show them a picture of a snake, and you're probably going to get some amygdaloid activation because we all get freaked out by snakes or spiders or things like, or you show them the picture of an angry face, a threatening face, and the amygdala activates also. You take somebody with social anxiety and their amygdalas don't particularly respond to snakes and forest fires and hanging by your heel and stuff like that, but hyper reactive. The amygdala is extremely reactive to faces with negative emotional valence and perceiving neutral faces as threatening as well. So you see, as one step there, the amygdala is hyperactive, seeing threats that other people don't, not just in all sorts of, but seeing social threats that other people don't. An amygdala that's particularly tuned in that direction. Okay, you see this in another part of the brain, one oh so many episodes ago, the dorsal lateral prefrontal cortex. What's it about? Executive function, decision making, impulse control, all that kind of thing. And what you see is you put somebody in a circumstance where they have to interact with a stranger. They're playing some sort of game together, one that requires them to cooperate, to trust each other, where there's the possibility of them stabbing you in the back or you stabbing them in the back. But over a bunch of rounds, you cooperate and you begin to feel more comfortable out the individual, and you are more likely to make generous offers. And that's what normally goes on. What's happening when that normally goes on? It's your dorsal lateral prefrontal cortex, which activates, saying, hey, do you notice you just had an exchange with the person and they didn't stab you in the back? Do you notice you've now had 11 of them in the row? Stop worrying about them. Stop perceiving them as a stranger. Begin to relax, get more comfortable with them, begin to pick up their positive, affiliative social cues instead of just seeming like they're scowling or something. You need your prefrontal cortex, and particularly this dorsal lateral. What do you see in people with social anxiety disorders in a circumstance like that? The dorsolateral prefrontal cortex doesn't activate as much. And that's a piece by which you don't habituate to novel social circumstances. Okay, so we've been looking at the neurobiology of how some people have extreme anxiety responses to novel social circumstances. Let's translate that a little bit and say we've been looking at the neurobiology of how some people's lives are completely crippled and made dysfunctional out of social anxiety. Because at an extreme, social anxiety, like other anxiety disorders, are totally disruptive of normal function. They make for tremendous amounts of misery and inability to function effectively, efficaciously, happily, calmly, feeling safe in the rest of the world. This is like a pretty disastrous thing to happen to you. Oh, yeah, one other piece of it is the hormone oxytocin, which has a lot to do with inducing trust and pro-social behavior. There's some suggestions that some families that have social anxiety disorders running through them have funny versions of genes associated with oxytocin, the oxytocin receptor. Okay, but back to, so we're looking at the nuts and bolts here about how stuff can go really wrong and make your life profoundly miserable. And thus, back to the second part of that question, not only why is social anxiety a thing, why did it evolve? Why it looks pretty damn maladaptive. You could make that more quantitative in a way that Darwin or a Darwinian would think, which is to say, well, does having an anxiety disorder decrease your reproductive success, decrease your likelihood of leaving copies of your genes in the next generation? And the answer is absolutely. Much like with depression, all the anxiety disorders are associated with increased risk of a number of cardiovascular diseases, risk of some metabolic diseases, shortened life expectancy, things of that sort. So, by the rules of Darwin, if you have a social anxiety disorder, that is something that sets you up for leaving fewer copies of your genes in the next generation. That's the definition of something you don't want to evolve. What's evolution about? Evolution is about good stuff like the giraffe who could have the slightly longer neck, got more leaves and had more babies, one of whom had an even longer neck, and on with this adaptive trait. And here we see social anxiety, along with the other anxiety disorders, being formally maladaptive from the standpoint of leaving copies of genes. What's it doing in us? Two flavors of explanations. And the first one I've been thinking a lot about in the last 15 days or so since the inauguration. Okay, so you look at an anxiety disorder. You are prone towards seeing threat that other people don't. And as a result, you have elevated blood pressure, cardiovascular disease. You pay a price in terms of Darwinian fitness. And thus, what you would predict is over long periods of time, people who have a heavy genetic load predisposing them towards anxiety disorders should be slowly selected against in the population because it's a maladaptive trait. Over long periods of time, there's selection against people with florid, incapacitating anxiety disorders, much as there's selection against people with severe depression. So that looks like come back in 10,000 years, and there should be no humans around who have an inch of anxiety in them because they've all been selected against. We've gotten rid until something happens. Jargon in the field, a selective bottleneck. Some sort of crisis comes up, some sort of disaster, some once in a century, once in 100,000 years sort of thing, where 99% of the population doesn't survive. And the 1% that does has a very specific trait. And that trait is now passed on in the surviving population and becomes far more common. Where does anxiety fit into this? And here's the metaphor I always use. If I were sitting around Berlin in 1933, I sure hope that I would have been prone towards anxiety rather than sitting there and saying, people are people, and those guys in the brown shirts and those weird armbands, you get to know somebody, we all have stuff in common, we got more things in common, more differences, and things blow over after a while, and this will be fine. Hell no, I would have said, this is not right. I am perceiving menace everywhere I look, and I'm getting out of here. And that was, in effect, a selective evolutionary bottleneck. The people who were the anxiety canaries in the mine shafts with the emergence of Nazism were the ones who said, I'm getting out of here. And everybody else wound up being vaporized in the ovens. So you get long periods of selection for this maladaptive trait of seeing menace all over the place. And then you get to the rare event where these are the only people who come out the other end. You get a scalloping pattern like that. So that's one possibility. The other one is another standard model for making sense of why are some maladaptive traits being passed on. They're having two different versions of a heritable trait. Jargon in the field, you can have a heterozygotic version of it or a homozygotic version. Let's translate that into heterozygotic. You've got a partial version of this genetic trait. Homozygotic, you got a major league version of it. And what do we see is get the homozygotic version of the genes relevant to this, and you have an anxiety disorder. You have social anxiety. You're crippled socially. It does horrible things to your life. It shortens your life expectancy. But have the partial version, and you're someone who's pretty good at reading the tea leaves and deciding, you know what, I think I'm going to just move over to this other spot here because I think I'm detecting that there's a comet that's about to hit that bench there, kind of thing. Not paralyzing anxiety, but instead people who are more cautious, pragmatic, uh, realistically pessimistic, perhaps. And that could be a very adaptive trait in all sorts of settings. And the argument then goes that as long as you have enough people who have the heterozygotic advantage of mild protective anxiety, this trait is going to be carried along, despite the fact that occasionally you get the cousin with the full blown version of the genetic disorder whose life is ruined by it. And when you do the math, there's more people with the advantageous heterozygotic version, the partial version, and it's the rarer ones that have the full blown version. And as long as the advantage here, the magnitude of the advantage times the prevalence of people with it, as long as that outweighs the disadvantage of the occasional cousin with the full-blown horrible version, this is not asking about the persistence of a maladaptive disease. This is a very adaptive trait, except every now and then you get a relative who's got lousy luck and they pay the bill for it and you get the advantages. So those are the two broad models: long gradual selection against, and then a rare event where suddenly it's majorly advantageous. Or this model where what we view as anxiety disorders is the homozygotic, the full blown genetic burden of these traits. And much more common in terms of gene distribution will be the relatives who have the milder version, where it could be adaptive to be a little bit on the cautious side and a little bit on the suspicious side. And showing human cognition reflects that we are much, much more likely to be sort of bothered by false positives than false negatives. If there's something rustling in the bushes, you probably want to be on the anxious side and just make a guess that it's a lion rather than like some birdie thing and act cautiously there. We are more likely to be biased in that direction. And that is more adaptive in lots of circumstances. So I think that's what's maintaining a genetic propensity towards anxiety, which is more or less common in different types of environments, blah, blah, the usual cautious stuff, where that's what's being carried along evolutionarily. And then there's the poor relative now and then who instead gets saddled with a full-blown version and their life is destroyed by it. I think that's what it's about.
And that's episode 53 for you. Keep submitting questions at the form found in the Instagram story highlight in bio or the YouTube video description. I'm Offspring Sapolsky, and thanks for your continued support of science and the beard.